Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy professor here at Foothill College, and it's a great pleasure to welcome all of you here in the Smithwick Theater and everyone listening to us on the web to this lecture in the 16th annual Silicon Valley Astronomy Lecture Series. This is our last lecture of the school year, and it's an especially exciting one. We're very pleased to welcome Dr. Stephen Kane of San Francisco State University, who's going to talk about finding a new Earth, exoplanets, and the habitable zone. Dr. Kane has been researching planets around other stars for more than 20 years, and he's discovered and characterized hundreds of planets orbiting other stars, including Kepler 186f, which is the smallest planet yet to have been found in the habitable zone, in the zone where water is liquid around a star. After spending many years working at the NASA Exoplanet Science Institute, Dr. Kane is now a professor of astrophysics at San Francisco State University. He is also the chair of the Kepler Mission Habitable Zone Working Group, a role which he's going to tell you much more about tonight. And he's the director of the Planetary Research Laboratory at San Francisco State University. He's a distinguished research scientist, but also really enjoys public outreach and education. He teaches seniors at San Francisco State. And so it's a great pleasure for me now to welcome to the Silicon Valley Astronomy Lecture Series, Dr. Stephen Kane.
Okay, thank you, Andy, for that introduction. That was fabulous. And thank you all for coming out tonight to listen to me tell you about some of the exciting discoveries that have been happening. I'm sure you've seen some in the news lately. And what I'm going to attempt to do tonight, and I'm sure this won't be a difficult sell, but to convince you all that we're living in pretty extraordinary times. And I'm going to be telling you about some significant thresholds in terms of science, and I would argue as a civilization that we have crossed over recent years. As Andy mentioned, I've been working on this topic for more than 20 years, and it was in the mid-90s that I started graduate school. At that point, I thought that I was going to be working on planetary science within our solar system, but then with the fabulous discovery of planets outside of our solar system, I realized the opportunity for an infinite number of worlds that I could be studying. So it's been very, very exciting to see the field develop over the past few decades. Now, one thing I wanted to really stress about this, and sometimes we forget due to the recent years when we've seen a lot of press releases and we've seen a lot of exciting discoveries, that the idea of planets around other stars and even how we can go about discovering them isn't new. And there are philosophers and scientists over many centuries who have posed this question about, are we alone and are there other planets out there? And so one of those is somebody who you may have heard of named Giordano Bruno. Now, Giordano Bruno lived back during the 1500s, and he was one of these people who was ahead of his time. And he was saying things that were quite controversial. But he said something in particular that resonates very closely with the topic I want to talk to you about tonight. And I'm going to read you this interesting quote of his. He starts out by saying, "There are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets of our system." Now, I need to pause there. As I said, this was during the 1500s. So he's talking about 7 planets. And you might want to pause for a moment and think about, well, what 7 planets is he talking about? He's talking about Mercury, Venus, Earth, Mars, Jupiter, and Saturn. So that's 6. He's not talking about Uranus, he's not talking about Neptune. They had not been discovered at this point. So the seventh one he was talking about was the moon, because this was a period in history when the heliocentric model of the solar system was still being accepted. And the models prior to that had the Earth at the center, with the moon orbiting the Earth and the other objects orbiting the Earth. So when he was talking about 7 planets, he was talking about the 6 planets known from antiquity, plus the moon. He goes on and says, we see only the suns because they are the largest bodies and are more luminous, but their planets remain invisible to us because they are smaller and non-luminous. The countless worlds in the universe are no worse and no less inhabited than our Earth. Now, the key sentence in this quote is the middle one, where he identified the key problem that was going to plague astronomers who try to find planets around other stars, and has continued to do so right into the present time. That is, he said that the planets are invisible to us. Why? Because they're right next to a very bright object, and they're lost in the glare of that object. Ideally, of course, what we would like to do is directly detect these planets. We would like to be able to take pictures of them. And that is something that we are progressing rapidly towards. But it is very, very difficult to do because they are lost in the glare. And so he recognized that direct detection is a significant challenge. And it is something that we've had to contend with all these years. Over the past century or so, there have been other ideas about how we can get around this problem that Giordano Bruno identified. And that is, if we can't directly see the planets, perhaps we can indirectly see them. Indirectly meaning that although we can't see the planet itself, we can infer its existence because the planet has an effect on the things around it. And the most obvious thing is that it has an effect on is the star that it's orbiting, because that is something that we can see very well and that we can measure it and infer the presence of a planet. So there are various ways in which we can do this. I'm not going to dwell upon all the different ways in which we discover planets around other stars tonight. I'm going to merely concentrate on 2 main techniques that we often use. The animations you can see on the screen right now show these 2 different methods, and the top one is called the radial velocity method, or the Doppler wobble method. Now, that is a technique in which we are observing the star and we see it move towards and away from us, and the amount that it moves is being caused directly by the mass of the planet gravitationally tugging on the star. Because although we often talk about planets orbiting a sun, then it's strictly speaking, what we really need to say is that the planet and the star are orbiting their common center of mass. Another example of that is, of course, the Earth and the Moon. The Moon orbits the Earth. Yes, of course it does. But really, the Earth and the Moon are orbiting the center of mass of that system. That means that the Moon is making the Earth wobble. Now, what we can do is we can measure this wobble. And it's something that we've only been able to do over the past 2 decades, or past 3 decades, but over the past 2 decades to the level where we can efficiently use it to discover planets around other stars. The bottom animation is one that many of you may have seen a lot recently, particularly in light of the recent press release. And that is something we call the transit method. So in this method, if the planet crosses the disk of the star, then it blocks out some of the light. Some of you may have also seen the transit of Mercury on Monday morning. I don't know how many of you were able to see it from here. Apparently it was overcast in San Francisco. I was fortunate enough to be down in Riverside in Southern California where I was able to see it. Somebody asked me at the time, so how much brighter is the sun going to be when Mercury finishes the transit? The answer is 0.001%. That's the effect that Mercury has on the brightness of the sun. You can easily calculate that yourself because it's just the ratio of the areas, the ratio of the area of Mercury to the ratio of the area of the sun. And that tells you that what you measure from the transit method is the radius of the planet. The top one depends on the mass, so you measure the mass of the planet. The transit method tells you the radius. Those two are very complementary. You put them together and you get a measurement of the mean density of the planet. And then you can do some exciting science with that. So in order to do this work, we've had to have technology catch up to ideas. And that's why the past couple of decades have been a real revolution. Not necessarily because many of the ideas have been new, although many of them have. But what we've really needed to do is develop the technology in order to pursue those ideas. One of the things we need to do is we need to use very large telescopes. This is showing some of the telescopes on Mauna Kea. And that includes the Keck telescopes, the Gemini telescopes, and we need to use these large mirrors in order to collect enough data from these stars in order to do the measurements to the accuracy that we need to do them. So this has been a real workhorse for the community over the past several decades. But in order to measure the change in brightness of a star due to a planet passing in front, ideally what we need to do is go to space. And in 2009, NASA launched the very first telescope launched by NASA that was dedicated solely to the task of discovering planets around other stars, and specifically learning about the frequency of Earth-sized planets. It wasn't deployed to an orbit around the Earth, rather it was deployed to what's called an Earth trailing orbit, where it could stare continuously at one patch of sky. And it was able to monitor about 150,000 stars continuously for a period of over 4 years. And so this is where most of our data for the transit method has now come from. It's come from the Kepler spacecraft, and I think you'll all agree with me that that has been a resounding success. Now, what I'm going to do now is I'm going to show you how much of a success it's been, because one way in which we can present the data is just purely in terms of discoveries and looking at how many discoveries have we made each year. Well, so this is a diagram where along the horizontal axis you're seeing the year that the discovery was made. On the vertical axis you're seeing the number of discoveries that were made that year. And I've broken it down here by color by the different methods that can be brought to bear on the problem. Now, the two that I've been talking about, the radial velocity method and the transit method, are shown as red and green. Radial velocity is red, and the transit method is green. So what you can see here is that we've been getting better and better at this, and we've been discovering more and more planets. And you can see that although in the beginning the Doppler method, the radial velocity method, was the dominant way in which we found planets, once Kepler launched in 2009 in particular, the transit method quickly started to dominate the field. And you can see the number of discoveries shown in green rapidly rising. What we can do here is we can point this out just to bring home the point of how important Kepler has been. As I said, in 2009, Kepler was launched. Then in subsequent years, they started to release the data. And that has produced an enormous number of discoveries. An interesting part of this diagram you'll notice is that after around about 2011, we see the number of planet discoveries go down, which is a little bit disconcerting. What's going on there? Are we starting to run out of planets? Did something break in our pipeline that was sending us the data? It wasn't any of those things. It was actually a symptom of how much data we were receiving and the amount of effort required to understand it, because we were essentially receiving a fire hose of data. And it took us a long time to try and understand it. The other part to this is that the radial velocity method, which was previously mostly being used for survey work, discovering new planets, those experiments, at least part of their time, was being brought to follow up the Kepler discoveries so that we could determine the mass of those planets as well as their radius, because those were smaller than any planets we'd found before. And so there was much more science to learn from that. Many of you will notice also that this chart is out of date. So what we need to do is get the latest data and see what changes. So this is what the chart looks like now. Some of you may have already seen the effect of the announcement that happened on Monday. So there have been a few things which have occurred here which have some significance to them. Firstly, in 2014, there was the announcement of 800 new confirmed planets from Kepler, and just earlier this week, there was the announcement of 1,200 new planets. Now, one of the things I should stress about this is that the way in which the Kepler system works is that it detects something which looks like it's a dimming of a star, and it classifies that as a candidate waiting to be followed up. And sometimes we need to do a lot of work to follow up each of the Kepler candidates one by one to confirm them. Once we do that, we move it from the candidate list to the confirmed list. Now, sometimes we develop very clever ways to confirm many, many candidates at once. And at those times, we can move many hundreds of candidates over to the confirmed list all at once. So I want to be clear about that, because you can sometimes get the impression that Kepler has all of a sudden discovered 1,200 new planets. What's actually happened is that these were candidates that we had sitting in front of us all along. We just had no way of knowing if they were real or not, or if there was something else going on that mimicked a planetary signature. And so these new clever ideas have allowed us to confirm many of these planets at once. And so now we're up to more than 3,000 planets that have been confirmed just over the past few decades. I'll show more of that in a moment. Before I show that, I want to show you a different way of looking at this data, because as I said, I really want to convince any skeptics in the room that this is an exciting adventure we're on right now in our lifetime. So what I'm going to do is I'm going to show you the data a little bit differently. Once again, on the horizontal axis, it's the date of discovery. And now on the vertical axis, I'm showing the mass of the planet. And so where you see 1, that is 1 Jupiter mass. And the reason that I've started with a Jupiter mass is because that's where the field started. When we first started finding planets, back when I was a young and wide-eyed graduate student, all the planets that we were finding were around Jupiter mass or larger. It was the low-hanging fruit, the planets that created the largest signals that we're able to find first. Now, what you can see there is that that's where our sensitivity started, and then as time went on, not only were we finding more planets, we got better at it. Now, another thing I wanted to point out about the vertical axis is that you can see it's on a logarithmic scale. So that means we didn't just get a little bit better at it each year, we got a lot better at it, and we rapidly improved our instruments and understanding the data. Now, as time has gone on, and since we've become so good at finding planets which are in smaller mass, you may well ask, where is the Earth? This is the line for the Earth. And we can all be very proud to say that as of a couple of years ago, we crossed a significant threshold. We crossed a significant threshold in that we now live in a civilization that can detect planets the mass of the Earth, and with Kepler, we can discover planets which are the radius of the Earth. And so this is very, very important for us. It's a very important milestone, because once we are able to discover planets of the Earth's mass and of the Earth's size, we can actually start to address a very, very important question which has gone back thousands of years, way back to Greek philosophers. And the question is, of course, how common are these planets? Now, as you saw from the quote from Giordano Bruno, he imagined that they were very common. And that's something which has been said many, many times, that the planets are the size of the Earth are probably extremely common. But we hadn't been able to quantify it. It was something that we needed to test, and we needed to test this rigorously. Well, before I quantify the answer to this question for you, let me show you what the distribution of Kepler candidates looks like. I mentioned that when we discover objects from Kepler, we first call them candidates. When we create a graph of the Kepler candidates, this is what it looks like. So on the horizontal axis for this plot, you're looking at the orbital period of the planet, how long it takes that planet to orbit its star. And when you look at the vertical axis, this time you're looking at the size of the planet. And once again, that's a logarithmic scale. And something that we often do is we use 3 units of measurement, very convenient units of measurement, and that is the Earth, Neptune, and Jupiter, because they are such dramatic size differences. And so the Earth is, of course, 1 Earth radius, Neptune is about 4 Earth radii, and Jupiter is about 11 Earth radii. So now we can, on this graph, we can put all of the data from Kepler and see what it looks like. And what you can see is that the planets of the larger size, even though we were discovering those first with the radial velocity method, appear to be not nearly as common as planets which are smaller in size. If you look down towards the bottom of the graph, you can start to see that the density of points is increasing and increasing, and it doesn't seem to show any sign of slowing down until you get to the bottom right. Now the question you would then ask is, well, is that real? Does that mean that planets which are the size of the Earth or smaller at long orbital periods, it looks like they're rare? But that's not the case. That is where we hit the detection limit of Kepler. The Kepler mission went for 4 years, and that means that many of the planets which are smaller and longer period just weren't within the reach. But it seems from the data that we have so far that that density of points will continue to increase as we go to smaller sizes. So, what is the answer to the question? The answer to the question is that terrestrial planets are extremely common and are some of the most common planets in the universe. This is extremely good news. This is extremely good news for habitability. It's good news for the possibilities of life elsewhere. And if you think back on it, then intuitively it makes sense. One way in which to think about it is to imagine a pile of rubble. And if we're looking at this pile of rubble, you see a few of the large boulders, and then you see a few more of the large rocks, and then many, many more of the small rocks, and by the time you get to the pebbles and the grains of sand, you can no longer count them. And it turns out that planet formation works in exactly the same way. You form fewer of the larger planets, you form many more of the smaller planets. And that's been reflected in what we've seen in the distribution of planets in the universe. So this is fantastic news. Like I said, the number of planets that have been confirmed is now over 3,000. And we still have around about 4,500 candidates waiting for us to look at in more detail. What I can tell you is that the work that's been done so far on the Kepler candidates shows that around about 90% of them are real. That's a very good rate of real planets to false alarms. And so that means in reality, our society has discovered well over 7,000 planets at this point. So this is a remarkable difference from when I was a teenager during the 80s, and we were sending missions out to the various planets of our solar system, which I was very excited about. It motivated me a great deal, but it's been very interesting to live almost equal amounts either side of this boundary of not knowing of any other planets other than the ones in our solar system, and now being able to stand up here in front of all of you and talk about more than 7,000. To me, it's still extremely extraordinary. Now, what I want to do is I want to start to tell you about more specifics about this search. And as I said, I've been working on this for more than 20 years. I've had the great privilege of being able to be involved in a lot of different aspects of the work. And the work that I do has more or less evolved into 3 main categories. And I can describe the categories as follows. The first category is planetary detection. That's the most obvious one. We need to have discoveries of planets to have things to talk about. But then you can ask the question, well, then what comes next? What do you do with those discoveries? And it turns out there's a lot we can do. What we can do is something called characterization of planets, where we think about in more detail the atmosphere of the planets. What does the atmosphere of the planet look like? What do the orbits of the planets look like? Are they different from the ones in our solar system? And we can ask those kinds of questions. One of the phrases that also amazes me that we can use today is exoplanetary atmospheres. We're not only finding a lot of planets, we're studying their atmospheres. And so this is also a very exciting time to live. And of course, the exoplanetary atmospheres is something which becomes extremely important when we start talking about habitability, which is the third part of my work. As we've been discovering more and more terrestrial-sized planets, then the question keeps coming up over and over again about, are these planets habitable? And I'll tell you a story about one of the very first planets that I discovered back in the early 2000s. And at that time, I was a postdoctoral scholar, and I was at the University of St Andrews in Scotland. And we discovered a planet which was fairly typical of the time, which is that it was a planet which was the mass of Jupiter, and it was what we call a hot Jupiter, which means it only took about 4 days to orbit the star. Now, during the press conference, what happened was we explained that this was a planet that was the mass of Jupiter or larger. It was so close to its star that it had a calculated temperature at the top of the atmosphere of about 3,000 degrees Kelvin. And during the question time, one of the very first questions we got was, do you think there could be life on it? I had to keep professional at the time, and I took the question seriously. But one thing, the things about that question that really struck me was that the real thirst for understanding the frequency of life in the universe and the association of life with planets, regardless of what the planets really look like. Now, once we start talking about terrestrial planets, then this becomes an increasingly imperative question. And so this is something that we need to answer. Now, how do we answer it? This is a difficult problem. I was saying to Bill just earlier, something which is often said is that, well, we don't really know exactly what life is, but we'll know it when we see it. And that's not necessarily true either. We need to be very careful, we need to be very smart about how we approach this problem. The main part of the problem is, of course, that we only have one data point. And that causes us to be very anthropic. We know what has worked here. We know it's worked at least once. And we need to try and get outside of that box. One of the ways in which we can approach this problem is to think about a particular property of the Earth which has been crucial to the evolution of life on Earth. And that is the vast amounts of liquid water. Another comment that is often said in this context is that, well, obviously water is important for life on Earth because everywhere we find water, we find life. Now, that comment on its own, although I don't disagree with it, it's insufficient because the Earth has been contaminated by life for up to 4 billion years. And so at this point in Earth's history, the life has burrowed deep into the Earth's crust. Wherever we find anything on Earth, we find life. This is actually a problem when we're trying to determine the presence of life elsewhere in the solar system. Because if we send a rover to Mars, or one day when we send a spacecraft to land on Europa and drill through the ice, the very last thing we want is for it to carry something with it. We do not want the rovers to Mars or the spacecraft to Europa to contaminate a potential ecosystem, perhaps a fragile ecosystem that has never seen anything from Earth before, to be exposed to that. So trying to decontaminate things that we send to Mars is hard because life is so prevalent on the Earth. So how important is water really? Well, as far as we know, everything on Earth relies on it. It was said to me once a while ago well, that's not true. There are some basic forms of life that can go into hibernation for 100 years. And I said, what happens after that? And they said, well, they dehydrate and die. I said, well, in other words, they need water. So everything needs water as far as we know. There is good news about water, and that is it is extremely common. We see it all throughout the solar system. Hydrogen and oxygen themselves are very common. But we see water all throughout the universe. We can see water vapor lines, molecular clouds. We can see cases of liquid water oceans elsewhere in the solar system. Europa is one example, which I mentioned before, and Enceladus is another one. But I'll talk more about those in a moment. But the good news is that liquid water is common. It is also a very neutral solvent in which to have biochemical reactions. And so liquid water, so far as we know, although it may not be unique, in other words, there could be other environments, other liquids which promote the formation and evolution of life, it has been very important for us. And it is common. And it is a great way in which you can have biochemistry occur. So from that standpoint, looking for other places that have signatures of liquid water seems like a good starting point in order to try and address this problem, since we know it worked once. Part of the reason that we're so obsessed with this is, as I mentioned, the case of Mars. Mars is different from Earth in many ways. It is half the size of the Earth, and it has a far less substantial atmosphere. And as you know, we've been sending a lot of spacecraft to Mars, and hopefully that will continue well into the future. And the reason that we're doing that, of course, is because we have very good reason at this point to believe that Mars once looked like this. This is an artist's conception, of course, but it's based on what we understand about the topography of Mars, in that it has low-lying areas in the northern hemisphere and not so much in the southern hemisphere. And there's very good evidence to suggest that it had liquid oceans in the past. Did it have liquid oceans long enough to have biochemistry occur? That's the question that we're trying to answer, and look for evidence of that kind of biochemistry occurring in the past. This is extremely important. This is extremely important because if we can find a case of an independent evolution of life under the assumption that Earth and Mars haven't contaminated each other, which they well could have, but if we're able to establish an independent case of life evolving, then this is obviously extremely good news about other independent evolutions of life, and allows us to start quantifying a question beyond the question of how common are Earth-like planets to how common is life in the universe. As I mentioned, there are other places for liquid water that we can look to. I mentioned Europa several times. Some of you may be familiar with a very small moon orbiting Saturn called Enceladus. And it was mentioned earlier that you've heard some talks from Carolyn Porter about that recently, and she's done a lot of great work with the Cassini mission on this. One of the things I particularly like about Enceladus is that it has what we call cryovolcanism. Cryovolcanism, just what we understand about volcanism, but it's blowing out water into space and feeding the rings of Saturn. It was pointed out to me that I shouldn't be using the word cryovolcanism because it mixes Greek and Latin and breaks certain rules of grammar, but I love the word anyway. I encourage everyone to use it. Cryovolcanism. So Enceladus is a fantastic other location in our solar system where we could look for life. Now, let's go back to this liquid water. How are we going to use this to address the problem? What we can do is we can try and use it to define something called the habitable zone. No doubt many of you have heard that phrase before, and you've heard it over recent years in the context of press releases. Well, it may surprise some of you to know that the term habitable zone has existed in the scientific literature since about 1959, when there was a first attempt to quantify what the boundaries of the so-called habitable zone were from UC Berkeley. And over the years, as computing power became more accessible and atmospheric models became more developed, there were folks during the 80s and the 90s who were bringing these climate models to bear on the problem of calculating the boundaries of the habitable zone, the region around a star where if you had a planet just like the Earth that had the same kind of atmospheric pressure, that the water could remain in a liquid state. Sometimes you hear it referred to as the Goldilocks zone, where it's not too hot, not too cold, it's just right. So the thing to notice, though, about this definition I've shown up on the screen is that I've highlighted two key words. They are could and if. So those are highlighted to really bring home the whole uncertainty in this endeavor, that we are approaching this problem from looking something which is just like the Earth, but that may mean that we miss a lot of things. And we have to keep an open mind about this. Another thing to keep in mind about this is that I've already mentioned several cases of liquid water in our solar system that would not be that are not in the habitable zone of our star. The reason we don't consider those cases is because those examples are all moons of giant planets. And what we're really using this for is a target selection tool to tell us where to look next. We need to find a planet that has a signature that we can remotely detect. If we cannot detect the presence of liquid water from a distance of about 10 parsecs, then it's of no use to us. We won't know it's there. And so we need a planet with an atmosphere. It is insufficient to have a moon orbiting a giant planet that even in our own solar system we can't tell necessarily that the liquid water is there without actually going there. So one thing to keep in mind definitely about the habitable zone is that when you see these press releases, that we need to be wary of what it is that we're talking about. And that's where this if and the could come into play. Now, sometimes you'll see a press release and it'll apply not so subtly at all that we have discovered planets that are habitable. And depending on who you're talking to, that there might be a great deal of confusion around that. That confusion is natural. The habitable zone implies the zone in which planets are habitable. That's not what it means. It means if a planet was like the Earth, it could have liquid water, and that's all it means. But when we're comparing the phrases planet in the habitable zone and a habitable planet, there is an enormous information gap between those two phrases, an enormous gap. And it is currently a gap which we cannot cross. And so you mustn't let anybody convince you that we've crossed it. We haven't crossed it. In the years ahead, we're trying our best to do so, but that is a discovery for another time. And what we're doing right now is we're working towards that. So we can present the habitable zone in a way that is very useful for us if we're not just talking about the sun, if we're talking about all of these different kinds of stars that we're observing with Kepler and trying to understand about what kinds of distances you'd need to be from the star in order for the planet to be in the habitable zone. Well, it would be very little surprise to any of you that it depends on the star. Because if the planet is in orbit around a cool star, then it needs to be very close to its star. If it's orbiting a very hot star, then it needs to be further away. And so the extent of the habitable zone depends on what kind of star that you're looking at. And on this diagram here, those are some little artist pictures of some of the planets which have been found in the habitable zone. One thing I do want to also mention as a gratuitous advertisement for something that I've been providing as a service to the community for some years now. Since I started working on the habitable zone, I realized that I could provide this information to the community and to the public. And so I have a website called the Habitable Zone Gallery, 8zgallery.org. It has pictures, some of the pictures that you've seen and will see in this talk are from that website. So you should feel free to go there and look at the movies and the updated information about which planets we currently know are in the habitable zone. So what I'm going to do for the remainder of my time is I'm going to present to you a few more caveats or a few things, extra things for you to think about. I've already told you that the habitable zone, when we talk about planets in the habitable zone, that is based purely on the Earth and may not even apply to a planet that's even the same size as the Earth in another system. We won't know for some time. One of the problems that we need to deal with is that, like I said, we're looking for this kind of a planet. This is, of course, the Earth. Now, our solar system has an amazing feature that we haven't seen in most other solar systems, and that is there's this extraordinary gap. And what I mean by that is extraordinary gap in size. So if I wanted to go to the next largest planet, the next largest planet beyond the Earth is Neptune. Earth is the largest terrestrial planet, and the next planet is Neptune. Neptune is about 3.9 Earth radii. And that's an enormous difference in size. So why is that such a disturbing thing? Because Kepler has told us that that's a little bit weird. If we look at the distribution of sizes from Kepler, then we see a continuum. We don't see a gap. We don't see a jump from something which is 4 straight down to 1. And when we look at different sizes of planets, so if you look at this diagram, you can see the Jupiter at about 11 Earth radii. You can continue down in size until you finally get to Neptune, which is 3.88 Earth radii. Then we need to continue all the way down to the very bottom left to find Earth. There's all kinds of planets in between. And how come we don't have one? And this is a difficult problem because we don't fully understand when a planet stops being terrestrial and starts being a gas giant, because we don't have anything in between. These are sometimes planets that we call super-Earths or mini-Neptunes. We have to make these ridiculous names because we don't have a planet in between. We could have had one. When the asteroids were first being discovered, several hundred years ago, with the use of telescopes, there was a thought that those asteroids were from a planet that had existed between the orbit of Mars and Jupiter, and something catastrophic had happened to it. There was a name for this planet. The planet was given the name Phaeton, and there was this whole history that was told about Phaeton. And that at some point in its history, catastrophe struck. That's not what happened in our solar system. We now understand that the reason that we don't have a planet between Mars and Jupiter is because it never could form in the first place, because of Jupiter. The effect of Jupiter, that's something which we call orbital resonances, but the gravity of Jupiter prevented formation in that gap between Mars and Jupiter. If not for that, Mars could have been larger, we could have had an additional planet, we could have addressed this problem, and we see them frequently elsewhere. You recall that from one of the earlier diagrams that I showed that giant planets are relatively rare, smaller planets are common, and we see many planetary systems that consist of mostly just small planets, and that's where we see these super-Earths, these mini-Neptunes. The problem with this is that we don't understand what their surfaces might be like. We don't know what the atmospheric pressures might be like, so we don't know how to use the habitable zone in those cases. So a lot of the time you'll see a press release for a planet which is only 50% larger than the Earth. Surely that must, if it's in the habitable zone, must have life on it. We have no idea if it even has a surface in the traditional sense. We certainly have no idea if it has liquid water on the surface, and don't let anybody try and even talk to you about habitability of the surface at this early stage. So that's something to keep in mind about this new learning curve we're going through in trying to understand these different kinds of planets. Fortunately, we are finding planets which are similar in size to the Earth, and one of those is the one that Andy mentioned during his introduction, Kepler 186f. And this is a planetary system where the outermost planet that we've discovered is only 10% larger than the Earth. That's something where we can say with a great deal of high probability that it is terrestrial. And since it is in the habitable zone, that's perhaps one of our best bets yet, although we don't know for certain. But it doesn't stop us from making beautiful, beautiful artist conceptions. In fact, I have seen the work of the folks at NASA who make these beautiful animations. So here's one where we're in a spaceship. We're flying through the Kepler 186 system, and this is using actual made-up footage of what this whole system may look like. You'll notice that the inner planets look fairly bland. We don't care about them. They're not in the habitable zone anyway. But we're going to go out to Kepler 186f because Kepler 186f is at the far side of the habitable zone. We've given it large ice caps at the poles. Maybe it's a little bit colder. We've got continents and oceans there. We don't know, but it's something for us to imagine based on what we know about the Earth. Once again, going back to our original starting point, our anthropic situation. Another question that sometimes comes up is having more than one planet in the habitable zone, because we do see that also. We see systems that have multiple planets in the habitable zone. And this has really inspired a lot of excitement from my colleagues who talk to me and say, wouldn't that be great to have 2 planets in the habitable zone and 2 independently evolving civilizations? We could talk to each other and everything would be marvelous. Well, so science fiction hasn't really borne that out as a good thing, and my argument to them is that having more than one planet in the habitable zone actually rules out the overall habitability. Now, there is a far more serious problem that we need to deal with, and that is the fact that if we are using a technique from Kepler to look at the size of planets, and that's most of what we learn about the planet, then we need to remember something, that we have an incredible dichotomy within our own solar system, and that is, of course, Venus and Earth. Now, the fact that I'm using dichotomy to describe a sample in which there are 2 data points, the foolishness of that is not lost on me. But the reason that I use dichotomy is because those 2 data points are so incredibly different that we need to be aware of what's going on with our sister planet. For those of you who don't know, the surface of Venus is around about 800 degrees or 850 degrees Fahrenheit, and it has an atmospheric surface pressure of about 90 atmospheres. It has sulfuric acid in the atmosphere as well. That means if you were to stand on the surface of Venus, you would be melted, crushed, and dissolved all at the same time. Also, one thing that I forgot recently, a colleague pointed this out to me, that it also has frequent electrical storms, so you'd also be electrocuted. So we know of an example of a habitable planet. We also know an example of hell, of what that looks like. And these 2 planets formed and evolved in the same solar system, perhaps with very similar starting conditions. And we need to understand what the difference is between Venus and Earth. How common is a runaway greenhouse, or at least a natural runaway greenhouse, not a man-made one. That's a different conversation. But how common does a runaway greenhouse occur on a planet which is the same size as the Earth? What this means is that when we look at our Kepler candidates and we find a bunch of planets which is the size of the Earth, that is equivalent to saying that we're looking at a bunch of planets which are the size of Venus. It's the same statement because they're the same size. And so we need to understand what the contamination in our sample is from Venus, analogs in our data. And this is something that will be revealed in years ahead because of telescopes like the James Webb Space Telescope, when we are learning more about their atmospheres. That will be the key that unlocks it. That will be the key when we start seeing these differences in atmospheres. and we're able to identify these strong carbon dioxide lines as opposed to water vapor lines, methane lines, the kinds of things we find in the atmosphere of the Earth. So this will be very interesting in the years ahead. One last example I wanted to give you of an interesting planetary system that has been discovered over the recent years, and that is the discovery of planets which are orbiting not one star but two. Now that, of course, has been depicted in science fiction for a long time. But it's always been something which has been a little bit of an Achilles heel for planet formation, because it wasn't absolutely clear that you could form planets in environments where you had more than one star. And that's a particular problem, since we know that perhaps as many as half as the stars in the galaxy are multiple stellar systems. Say, for example, one of our nearest neighbors, Alpha Centauri, has a companion. And we don't. Are we just fortunate? Does it even matter? And what we've found is that these systems can also have planets. The Kepler mission has identified numerous planetary systems which are orbiting two stars, which are very close together at the center. So that's been incredibly exciting. What does that mean for habitability? That's something that I tried to address a couple of years ago. I calculated the extent of the habitable zone for two stars instead of one. The difficulty with that is that everything's dynamic. These stars are orbiting each other, the planets are moving, everything is moving, and so the habitable zone keeps moving. It's pulsing in and out. And so trying to understand this was difficult. But I published these results, and it attracted the attention of some of the media, and some of these planets are referred to as Tatooine because of the connection with Star Wars, of course. And when I've spoken to media over the years, I've learned that many of them just want 2 minutes of your time, just ask you a couple of questions, and they're done. They're in a rush. Some reporters want to sit and talk to you for an hour, and in those cases I'm absolutely happy to do so, but you become very relaxed and you say things you shouldn't. And sometimes they ask you the question that you shouldn't answer. And so I spoke to a reporter for an hour, and I thought that I'd given layman answers to the questions, and it all went rather well. And then at the end she asked me, so do you think Tatooine from Star Wars is habitable, yes or no? And it turns out I had been thinking about that earlier in the day, and I was feeling cynical at the time, and I had looked at this picture of Luke Skywalker looking at the setting suns, and I said, I don't know if you can read that text there, but basically what I was saying was, well, if you look at the angular separation of those two stars, you can calculate the extent of the habitable zone. And what we find is that Tatooine, not only is it not in the habitable zone, it's probably not even in a stable orbit. And George Lucas wouldn't have known that when he made the films. The research wasn't done at the time. So the article all became about NASA scientist says Tatooine isn't habitable. And the amount of hate mail I received, I keep because it's hilarious. But I learned that it's not just politics and religion, that Star Wars and Star Trek are off the table as well. So, all right, so now I want to finish by just telling you what's coming up. There are a few missions that I'm working with now, and there are exciting times that lay ahead. And what I've shown on this slide here mostly, well, they are all artist depictions, because these are talking about missions which are mostly not launched yet. The first one in the top left is an interesting one, because it's not actually an exoplanet mission. In fact, it's not even NASA. It's NOAA, the National Oceanographic and Atmospheric Administration, climate scientists. They launched a satellite to a point between the Earth and the Sun to monitor both stellar activity and the Earth and take continuous pictures of the Earth. Well, in my infinite wisdom, I decided to annex this climate satellite, and use the data to study Earth as an exoplanet. Because it was actually a very interesting time, and still is. Some of you may have seen the beautiful pictures it's produced of the entire daylit side of the Earth. What we can do is we can reduce that data to a single pixel to simulate exactly what we expect to receive from future imaging missions of exoplanets, and see if we can recover things like the rotation rate, the Earth's obliquity, because these are key things which affect the climate and the habitability at the surface. So in the top right is a very exciting mission called the Transient Exoplanet Survey Satellite, sometimes just referred to as TESS. It's going to be doing what Kepler did, but for the entire sky, for the brightest stars in the sky. And that's fantastic because since they're the brightest stars, we'll be receiving very high quality data and we'll be able to follow them up in ways that we haven't been able to do with Kepler stars. The bottom left will be the telescope that follows up TESS stars, and that is, of course, the James Webb Space Telescope. The James Webb Space Telescope is going to do extraordinary things for studying the atmospheres of exoplanets. And this is actually a key point where we come back to why the habitable zone is so important. Because very selfishly, from my own science, I would love to think that the James Webb Space Telescope is a dedicated exoplanet mission. That is not the case. It is a general purpose instrument that will be heavily oversubscribed. And so what's going to happen is that the community is going to need to make tough decisions. The time allocation committee for the JWST will come to the exoplanet folks like myself and say, give me your 5 best targets. And that's what we'll do. And what I'm going to do is I'm going to tell them to look at the ones which are in the habitable zone, because those are my best chance of seeing something which looks like a signature of biological activity. Ultimately, what we want to do is sample all kinds of planets, and we will eventually. But with limited resources, the first thing we're going to do is look at the planets in the habitable zone, and that's what it's for to give us a place to look in order to actually test these ideas. The last one on the bottom right is a European counterpart to TESS, which I'm also involved in, called Cheops. And that's going to be launched, all 3 of TESS, JWST, and Cheops will all be launched in 2018. So this is right on our doorstep. These new data sets are coming. And so this will be exciting years between now and the end of this decade, when we'll be learning even more about the planets we've been discovering. So the final thing I want to say to you all is the part of the interesting aspect of this, the way in which exoplanets, I've seen it evolve over the past several decades, is how the whole field has started to merge the disciplines. When I started, I was a pure astronomer. I had no idea how to talk to a geologist, and in many ways I still don't. And I was discovering planets which were the mass of Jupiter, and I didn't require, really, those conversations. Now we're discovering planets which are terrestrial in size. And there are communities, the planetary science community, climate scientists, geophysicists, who have been studying terrestrial planets for a long, long time. And there is absolutely no sense in reinventing the wheel. And so what's happening right now, what we're seeing happen, is that exoplanets is hitting a wall in the limit of its ability to characterize planets that are terrestrial in size. But the good news is there are many people who do know how to do that. So what we're seeing right now is that in the years ahead, when I start to gather data that shows a signature in the spectrum of an atmosphere, I won't know what that means. But the person down the hallway in the geophysics department might. I'll go to him and show him that signature and say, what does this mean about what geological processes on the surface could produce that in the atmosphere? And it's a very exciting time to have this collaboration between these people in different disciplines. And so even though some of us have been dragged kicking and screaming to the table to try and understand each other's dialogue, it has made a lot of progress. And so it's great that this is happening. And because what I've shown you in this talk is that, as for example shown on this slide, is that planets can have a similarity in size, but that's where the similarities can end. And this is what we need to understand in the years ahead. The final slide I wanted to show you was just the web page for my research group. Andy mentioned that I'm running the Planetary Research Laboratory at San Francisco State. It has a very easy URL, exoplanets.sfsu.edu. If you wanted to know more about my work and the work of my students, you're more than welcome to go there. And certainly contact me if you need any information about anything I've said tonight. Certainly there's a lot of ground I wasn't able to cover, but then that's what the microphones are for. So on that note, I'd like to finish there and encourage any questions. Thank you very much.
Hello. Thanks a lot for your demonstration. It's really enriching. So I had a question regarding Tabby's star, which is considered the most mysterious star in the universe. So there was a speculation based on the dimming of the starlight that there could be alien megastructure building around it. And recently I read an article saying that there is no alien megastructure there. It's just natural process. Yeah. So my question is, how do you determine if it's natural process and not alien megastructure building up?
Yeah, so that's a really difficult question to answer. I mean, the whole story of Tabby's star is extraordinary. Tabby is a very good friend of mine, and I know her well enough that I should have expected when it happened that she published the paper, and the title of the paper was "Where's the Flux?" It wasn't until about a month later I realized that spelled out WTF, which was really the sentiment of the community and has been ever since. I've seen a lot of ideas posed about what's actually going on with that star. Of course, there's the alien megastructure. There's another colleague of mine who, when the media approached him about this, the way in which he put it was, well, it could be an alien megastructure. It's the very last thing we would consider, has a very low probability, but that's on the table. And this is an example of what you shouldn't say, because the way in which that reported was, astronomers says there's a chance it could be aliens. After it went through the filter, that's what came out the other end. And so it's been a media extravaganza ever since. The other genius part of that is that when that news story broke, Tabby's star had set. It was on the other side of the sun. And so we weren't actually able to get any real follow-up for many months later, during which time we had a field day trying to address these questions. But I'm kind of skirting around your actual question, which is how do we address this? And you may have also seen that there's been attempts to look back through the Harvard photographic plates of the sky. There have been various papers about that saying that it may have been, the star may have been dimming, maybe not. My feeling is that the universe throws us so many curveballs that the fact that it may be something that we currently have no physical explanation for, I think is a completely reasonable thing to say. I think this is one of these situations where if we just simply say, I have no idea what's going on, and leave it at that, then we should be okay with that, as opposed to preferring a conspiracy theory over no theory at all. We should be content with no theory until we have more data. So that's what I'm waiting for.
Thank you.
Oh, yes.
Is there a reason we would have to assume that a planet, say as massive as Jupiter, would have to be a gas giant as opposed to a more solid planet? In other words, is there a reason that you can't have a more solid rocky planet the mass of Jupiter or the size of Jupiter?
Yeah, certainly there can be outliers in when you plot the data of the mass and the radius of exoplanets. As I said earlier, that allows you to calculate the mean density. And what we've found so far is that when you look at the density of planets that have both mass and radius measured, we find that the density increases up to a certain point at around about 1.5 Earth radii, and then the density starts to plummet after that point. The reason the density is plummeting is, of course, that they're starting to have large gaseous atmospheres. But your question is, but could we have something which is a larger radius and yet remain solid? And the answer is yes, we can have that. We don't think that they would form that way, but we have seen cases of planets which are relatively large, say around 2 Earth radii, and they are very close to their stars. In those cases, we think that the rich hydrogen-helium atmosphere that they may have formed with has been blown off. And so some of the planets that we're looking at, which are very close to their stars, are literally the cores of giant planets. Oh,
yes. Hi. I have a question. One of your earlier slides in your deck showed the distribution of how planets were discovered. And there's a little nugget in there on one of them that showed that pulsars were used to discover some. And from back here, I couldn't see the distribution of how many they were. It's kind of invisible. But I was just sort of curious if you had maybe a backup slide, or you could talk a little bit more about how pulsars or pulsar timing is used to discover.
Right, yeah, thank you for mentioning that. So what he's referring to is if you look at the year 1992, you can see a very small number of planets that was discovered there, and you'll notice the color of that is not red, it's orange. And the key will tell you that that's pulsar timing. Now, that was when I was just starting undergrad when that event happened. And pulsar timing, that's planets which are orbiting the remains of a giant star which has exploded. Sometimes when a giant star explodes, it leaves behind the remains of the star, the core of the star, which we call a neutron star. And neutron stars can spin very rapidly. And as they do so, they send radiation beams towards the Earth, which we can measure. Now, if there are any planets orbiting that neutron star, what we call a pulsar, and if there are any changes in the times of those pulses reaching us, then we can deduce the presence of a planet in the same way as we do with the radial velocity method. Now, the reason that, or part of the reason in 1992, when those discoveries were announced, it didn't get the attention that it deserved is because it caused people to scratch their heads a lot about, firstly, how could you have planets still existing around a star which has exploded as a supernova? That doesn't make any sense. Those planets shouldn't be there. And the second thing is, even if it did make sense, we certainly don't expect to find any life on them because they would be sterilized or something like that. And so that technique has revealed a handful of planets, about 4 or 5 planets from the pulsar timing method. Any more questions, David?
Yeah, the transit detection technique, whether by Kepler or some other instrument, seems to inherently depend on the line of sight from us to the star being roughly coincident with the orbital plane of the exoplanet, and those two things would seem to be, I would guess, pretty much uncorrelated. So is it fair to say that for every exoplanet we discover, there are maybe 4 or 5 more that we can't see because of this effect?
Yeah, that's one of the main problems with the technique, and it's actually part of the reason why people took so long to try it, because what was being said is that in order for a planet to transit its star from our perspective, its orbit has to be exactly aligned towards us. That seems like an extremely low probability event. And it is. It is a very low probability event. What's the solution? The solution is a brute force approach. It's where we just observe as many stars as we can, which is what Kepler did, to increase our yield. So what that means is that when we have a whole lot of planets, I told you 4,500 Kepler candidates from about 150,000 stars. Is that complete? Absolutely not, because those are only the planets which just happen to have their orbits aligned towards us. So what we can do is, like you were suggesting, is use just imagine that these orbits are randomly distributed and then try to calculate, if this is how many planets we've seen, then this must be how many planets we haven't seen. And so trying to address the completeness of our survey becomes a difficult task with the transit method, but it is doable, especially when you have many discoveries that allow you to do a statistical analysis, a proper statistical analysis.
Would you say a few words about the exciting Kepler results of starlight variations that were not planets?
Oh, sorry, the Kepler results that are not planets.
Yeah, the astroseismology and other things like that.
Yes, right. So when I first introduced the Kepler mission, I mentioned that it was the first NASA mission that was dedicated to the task of discovering planets around other stars. But that has certainly not been the only thing that it's done, because what Kepler has really provided us with is with high precision measurements of the brightness of 150,000 stars over 4 years. This is something which we can do all kinds of science with. And he mentioned astroseismology, which is a good one, which is astroseismology, for those of you who don't know, is essentially what you might imagine, especially living in the Bay Area. It is star quakes, because stars are vibrating due to the reactions that are occurring inside of them. And so we can learn a lot about the interior of stars by measuring the changes of brightness in astroseismology. In addition to that, there have been discoveries of white dwarf stars, which are stars which are like a star like the Sun, which is at the end of its life and is only about the size of the Earth. So it's intrinsically very faint and difficult to see. But Kepler has discovered a number of those. So there's a lot of publications which are resulting from the Kepler data, which is extraordinarily rich, not just in discovering planets, but our understanding of stars of different kinds as well.
So on this same graph here, you're showing the some examples that are from imaging. And I think if I can see the graph right, it looks like the first one is 2004. So I'm just wondering about that, what the source is. I know that the Gemini planet imager using the adaptive optics captured some amazing actual images of exoplanets last year, and I was under the impression those were among the first. So what's the imaging sources of these earlier results?
Right. Yeah. So imaging has always had the problem that I mentioned, Giordano Bruno mentioned, and that is the challenge of trying to essentially remove the light from the host star so that you can see what's left. The technological challenges of that have progressed pretty strongly with time, and in the earliest days, when you can see in some of the years like 2004 and 2006, there have been some imaging discoveries. Those kinds of planets which have been found in those cases are planets which are very, very young, and they're a long, long way from their star. So if you compare it to our solar system, where the outermost planet, Neptune, ignoring planet 9 for the moment, Neptune is about 30 AU away from the Sun, but we're talking about sometimes planets which are several hundred AU away from their star. And the significance of them being young is that they are still cooling off. They have a lot of their internal heat from formation, which means that they are producing a lot of their own emission. What this means is that when we try to image these systems, where we have a significant advantage because the planet is a long way from the star, so it's easier to ignore the effect of the star, and the planet is luminous. So when we look at those earlier discoveries, we're looking at planets which are of a particular demographic, and they're of a particular age. A lot of the planets from the other methods are very similar for planets of our own solar system, which have been around for several giga-years, they've cooled off, they've reached stable orbits. Most of the time when we're looking at imaging planets, up until the current point when, like you said, there's fantastic new instruments coming online, like the Gemini Planet Imager, and where we'll be entering more into a realm. One thing I didn't mention when I was talking about future missions is that there are other imaging missions planned, like WFIRST, eventually a mission called HabEx, which will eventually achieve Giordano Bruno's goal of imaging an Earth analog at 1 AU. But so far it's been of a very different kind of planet.
Is the habitable zone simply a function of the distance from the star, or do you consider other properties? If so, what? And for example, you mentioned in our own solar system, we're looking at our own moons around Saturn and whatnot. Can we detect exomoons?
Both good questions. The extent of the habitable zone, what we tend to do is we calculate what the extent of the habitable zone is at the present epoch. And that depends just purely on the properties of the star. It depends on the temperature of the star, how luminous the star is, what kind of a star it is. But your point about the age of the star is an important one, because small stars live a very long time. Massive stars don't live very long at all. And more to the point, during the lifetime of a star, its brightness changes. So if you look at the brightness of the sun as a function of time, the sun has been gradually becoming more luminous. So if a star increases in temperature and luminosity as it ages, that means the habitable zone slowly moves outward. And so you can start to think about something called the continuously habitable zone. What region around a star is continuously the habitable zone during the entire lifetime of the star. And so that's how it affects the boundaries of the habitable zone. Your question about exomoons, that's one of the next big things which are coming. Obviously, from our own solar system, we know that giant planets tend to harbor a lot of moons. There's no reason to think why that wouldn't be the case elsewhere, but that's at the very threshold of what we can detect at the moment. In principle, the Kepler photometry is good enough to see the signatures of moons. As a giant planet crosses the disk of a star, the moon will be there as well. But there's a lot of difficulties involved with that, because every time the planet crosses the disk, the moon will be in a different place because it's orbiting the planet. There's all kinds of complications with that. And so we haven't discovered an exomoon yet, but once we hit that threshold, we're going to probably be announcing much bigger hauls of moons than we are currently of planets.
You said that Kepler measured about 150,000 stars. What's the total number of stars in the volume of space that Kepler was able to survey? And also, what's the distance to the furthest star that it measured?
Yeah, so the way in which Kepler has been observing the sky, it's been observing a very faint group of stars, and that was by design, because we wanted to fit as many stars into the field of view of Kepler as we could. But the result of that is it means that Kepler essentially stared along a cone that extends from us out to about 1,500 light years. To give you an example, the Kepler 186 system is about 500 light years from us. But they're not close to each other at all. This cone extends way, way out. The difference with something like TESS is that it will be looking primarily in the solar neighborhood.
What is microlensing? Is that related to like curvature of space? The microlensing is...
Yes. Yeah. Thanks for bringing that up, actually, because microlensing is very dear to my heart, because when I started graduate school, that's the technique I started out using, microlensing. And microlensing is very interesting because it was something which was the topic of general relativity, and Einstein wrote a paper about it. He actually did it as a favor to a friend. He wasn't going to do it, but there was a friend of his that was bugging him about, well, could we see this effect that you've been talking about in general relativity of the light being bent by some foreground object? So he wrote a paper about it in a very negative tone because he said, well, we're never actually going to be able to see this because the chances of two objects passing close to each other is just so remote. Well, of course, with new technology comes new opportunities, and during the early 90s, there were various projects which started to look for this by looking towards the center of our galaxy where we have a high density of stars. And the premise is that if we're looking at some star towards the center of our galaxy, then we may have a closer, fainter star that passes in between. The light from the background star bends around the star that's closest to us, and it makes the background star gets brighter. Now, you can use that to look for planets because if the star in the foreground has a planet around it, it also deflects the light from the background star. And this is also considered another beautiful proof, if you like, of general relativity, because the data that we've observed in the way in which this happens is exactly as predicted by general relativity. And there have been about, I want to say about 20 planets which have been discovered from microlensing.
And that actually increases the brightness, the apparent brightness of the star as a planet passes in front, as opposed to decreasing.
Yes, increases, always increases. Yes.
Okay, last question.
Do you think there could be any life in planets bigger than Earth or smaller?
So I'll give the short answer to that, which is yes. But that's a very unsatisfactory answer. A better answer. I think that in general, life is extremely common in the universe. And I'm not saying this in a way of just waving my hands and saying, wow, there's so many stars, there must be life everywhere. You hear that argument all the time. And I don't know about you, but I find that argument very unsatisfactory because it's not really saying anything. But we can talk more about how we can say that better. We know that life on Earth started very soon after the Earth formed. I've already told you that water is extremely common. Turns out all of the bioessential elements, not just hydrogen and oxygen, but nitrogen and carbon as well, things like phosphorus, are extremely common. So that's good news. So I think that anywhere that life can take hold, it's probably there. Intelligent life is a different kind of a question. I'm not necessarily saying intelligent life is common, but I do think that life in general is everywhere. So with a planet which is larger than the Earth, say something which is 50% larger than the Earth, in the words of Jeff Goldblum from Jurassic Park, life finds a way. And I think over time we will find evidence of that. That's my personal opinion.
Thank you very much.